now you can actually have different SMs working on different kernels at the same time. So in your application, you can now instead say, I'm going to have these guys working on this workload, these guys working on this load, and the kernels can actually be cooperating somewhat. So really what that translates down to is, if you're writing a C program, you've got one function that's working on these sorts of things, and you've got another function that's filling up all this, the rest of this hardware, and those functions can communicate and cooperate.
This is a little side note, but what's the gigathread used for?
Oh, gigathread. So yeah, this is Marketroid speed, but basically this is our scheduling system, and the scheduling system is responsible for being able to handle this concurrency. It's also responsible for things like context switching. Context switching is basically when you're going to kick one kernel out and put another kernel in, you've got to figure out how to change the state. And if you're going to switch one whole application out and switch another application in, you've got to switch the state. And that switching of state is context switching. The CPU has its own version of it. The GPU has a different version of it. And they're similar in concept, very different in execution. But it turns out, traditionally, context switching is very expensive. And we're very aware of how expensive it is. So if you've got one CUDA program running, it's fast. But if you've got two, it's not that each one is running half as fast. You could actually get worse, in some cases maybe significantly worse than half as fast performance. Same thing applies to graphics. If you're running two contexts, graphics contexts, and if you're switching back and forth between them a lot, you can lose a lot of perf. And so we spent a lot of time trying to make sure that the scheduling systems and the switching mechanisms work very fast. And so instead of taking a millisecond, you take 20 microseconds, and that makes a huge difference.
You said that the context switches work between kernels as well, so if one kernel goes in, one kernel. How does that work with if kernels are passing messages to each other?
Well, so the kernel level context switching is more a matter of laying out, changing what a given streaming microprocessor is doing. So let's say you've got kernel 1 and kernel 2, and you want to switch out kernel 2 with kernel 3. So this guy's been running kernel 2. Suddenly you've got to change the scheduler, the dispatch, clear out the instruction caches, things like that, and have it point elsewhere. But all of the other SMs that are still working on kernel 1 can keep plugging along while you're doing that. So in that sense, it's separate, whereas if you're actually switching out a whole application, you're going to do it across the board for every SM in your system. So, I don't know.
But I'm saying if kernel 1 depends on kernel 2 and they're passing messages to each other, do you switch out both kernels, or how does that work?
Well, not necessarily. So synchronization in GPUs is handled primarily with something called a semaphore. It's not a semaphore in the traditional sense that you're used to thinking of kernel level UTXE type semaphores. It's not as atomic as that in some ways. What it is you can kind of think of it as an ever-increasing number. And when some work unit on the GPU is done with something, it'll increment this semaphore, which is just some chunk of VidMap. And then some other process will be waiting on this semaphore to reach a certain value or greater, or is just a set specific value. And so the way the kernels typically communicate is one kernel will be waiting on a semaphore to reach a certain value before it can go on. And the scheduler knows that this kernel is waiting. So if the kernel's waiting, the scheduler will kind of deschedule this kernel and let some other kernel pop in that can do work. And then once that semaphore reaches a certain, that preset value, then the scheduler knows, all right, we can put this kernel back to life and kind of switch things around that way. Yeah.
So is this concurrent kernel execution, is that new for Fermi then?
Basically, yes. There may be some exceptions that I'm not aware of previous to Fermi, but this is basically a new thing for Fermi. It requires largely different hardware to handle it. You might be able to fool it in some cases, but certainly widespread standard use, this is new for me. Oh yeah, a couple things I'll mention really quick. 40-bit address space. Internally in the GPU, ever since G80, we've had a 40-bit address space, which means traditionally in the GPU, memory was laid out in a very simplified way, which is that you've got this giant chunk of frame buffer, and everything goes in that giant chunk of frame buffer. And you address it physically. So, I know that I'm 3 megabytes into the frame buffer, so I just pass in a 3 megabyte offset, and that's it. And you've got to be able to handle offsets as big as whatever your frame buffer is. So if your frame buffer, if your VRAM is only 128 megs, then you only need, what is it, that's like 17 bits of address space. If you've got 512, well, you need 19 bits. 40 bits gives you 1 terabyte. Obviously, we're not going to have a terabyte of RAM on here anytime soon. So what that really implies is that under the hood, we've got a virtual memory system for the GPU now, which is the case. And everything that implies, we've got an MMU, which is a memory management unit. We've got page tables, we've got page table handling, we've got all sorts of specialized hardware. The driver does all kinds of crazy things with managing that memory. But for a long time, it wasn't efficient to work on 40-bit stuff. Really 64-bit, I mean, that's how it's passed around, but it wasn't efficient to do computations on 40-bit stuff, so a lot of the compute stuff under the hood, in order to run fast, you pass in a 32-bit address, and it would know what the starting offset was, and add that 32-bit offset to the starting offset and do all your work. And so you were kind of confined, though, if you were doing general purpose compute stuff, to this weird 32-bit range. And there were a lot of non-unified things before Fermi. Now pretty much everything in Fermi, texture, instruction, any sort of access, whether it's VRAM or sysmem or whatever it is, we can refer to it all using the same 40-bit address space, which is one of the ways that we can let kernels share information between kernels or between blocks in a kernel or between threads in a block, things like that. Unified address space really allows us to do a lot of cool things. And this, by the way, is what allows the use of C++ and CUDA. It now means that you can actually have virtual functions with CUDA, and you can go grab out of general VRAM the function you need from to cache and everything like that. I won't beat it too much beyond that, but atomics. One of the key things with parallel stuff is sometimes you need to do atomic operations. You might need to do an increment, a decrement, specialized shift operand, things like that. And you want to guarantee that when you read it and modify it and then write it, nobody else is going to modify it during that whole time span or even read it. It's got to be, as far as all threads are concerned, this has to be an instantaneous operation. And so GPUs traditionally were not very good at that. It's not something we were set up for. And so Fermi, we've now spent a lot of time working on that. And we can actually do much faster atomics than we could in the past. I can't tell you how this compares to a CPU because I simply don't know. But I do know that it's just one more example of how we're getting a little more general purpose to allow people to do non-graphics things. Like this isn't important for graphics, but general purpose stuff, it's very important. And lastly, DMA engines. Traditionally, the GPU, if you're transferring things across the bus, we're kind of stuck waiting for that transfer to finish before we go on and do our computation, graphics, or whatever. And it becomes much more important if we're trying to get a lot of throughput on, that while compute is chugging on this workload over here, or while graphics is chugging on the workload, we need to plan ahead for the next workload. We need to be transferring data from sysmem across the bus now so that it's there when we need it. And if we need results back to the CPU, we need to start transferring it as soon as we're done.